Hey everyone, welcome back to the channel. Today we're diving into a mind-blowing discovery that won the 2025 Nobel Prize in Physics. Three scientists, John Clarke, Michel H. Devoret, and John M. Martinis, all working in the United States, were awarded this incredible honor. Their prize? For the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. All right, that's a mouthful. But don't worry, let's break it down in a way that actually makes sense. Quantum mechanics is the science of the tiny world. Atoms, electrons, and other particles smaller than we can see. Usually, these particles behave in very strange ways that don't follow the regular rules of physics we experience every day. For example, a particle might tunnel through a wall instead of bouncing back. It might exist in two places at once, or it can jump from one energy level to another without passing through the space in between. All of that seems impossible, and yet it happens in the microscopic world. But here's the problem. These effects are normally only visible in super tiny systems, like atoms or photons. So the big question scientists have had for decades was, can we actually see these weird quantum behaviors at a scale we can hold, something visible and measurable? And that's exactly what these three scientists managed to do. First, we have John Clarke, a British physicist from the University of California, Berkeley. Next, Michel H. Devoret, a French-born scientist working at Yale University. And finally, John M. Martinis, an American physicist from the University of California, Santa Barbara and QLab in Los Angeles. Together, their research changed how we think about quantum mechanics by showing that the weird quantum world is not just for the microscopic, it can happen in macroscopic systems too. Their breakthrough came from an experiment that, at first glance, looks simple. It involves a special kind of electric circuit using superconductors. Let's explain this step by step. A superconductor is a material that can carry electricity without any resistance when cooled to very low temperatures, close to absolute zero. That means no energy losses heat and 100% efficient current flow. Now, the scientists built a circuit made of two superconductors separated by a super thin layer, something that normally does not conduct electricity. This setup is known as a Josephson junction. Under classical physics, no current should flow through that barrier because it's an insulator. But when they observed it at low temperatures, something incredible happened. They found that electrons, grouped together in something called Cooper pairs inside the superconductors, were able to tunnel through the barrier, even though classically they didn't have enough energy to cross it. Imagine a ball rolling up a hill. If it doesn't have enough energy to go over the hill, it should roll back down, right? But in quantum mechanics, there's a tiny chance the ball just disappears from one side and appears on the other. That's quantum tunneling. Now, for the first time, they could see this strange behavior happening in a real, visible electric circuit, a macroscopic system made of trillions of electrons working together. It wasn't just theory anymore. They proved it in the lab. The second thing they discovered was energy quantization in the circuit. Normally, if you increase the energy in something like a swing or a guitar string, it can take any amount of energy smoothly. 1 joule, 1.5 joules, 1.6 joules, whatever. But in the quantum world, energy doesn't come in a smooth line. It jumps in steps, or quanta. It's like a staircase, not a ramp. In their superconducting circuit, the electrons didn't absorb or emit energy continuously. They did it in discrete packets. That's what energy quantization means. And remember, this was happening in a circuit you could literally hold in your hand. That was the shocker. They brought a strange microscopic quantum effect into our everyday world. So why is this discovery such a big deal? Because it opened the door to an entirely new technology, superconducting quantum circuits. These circuits are now the foundation for quantum computers, the next revolution in computing. Instead of bits that are either 0 or 1, Quantum computers use qubits, which can be both 0 and 1 at the same time, thanks to quantum effects like tunneling and superposition. The work by Clarke, Devoret, and Martinis provided the first direct evidence that these quantum effects can be controlled and scaled up in electrical systems. They showed that it's not just theory. We can build systems that use these effects. And that's exactly what modern quantum computing companies like IBM and Google are doing today. In fact, John Martinis later led Google's quantum computing team that achieved quantum supremacy in 2019. Their research also impacts quantum sensors, devices that can detect incredibly tiny magnetic or electric fields, and quantum communication, where information is passed securely using quantum principles. Let's recap with an analogy. Imagine a skateboarder at the bottom of a halfpipe. In the classical world, if they don't have enough speed, they'll never reach the other side. But in the quantum world, there's a small chance they just appear on the other side. That's quantum tunneling. And when they do tricks to gain energy, they can't move up the ramp smoothly. They can only jump between certain hard-set levels. Energy quantization. When Clarke, Devoret, and Martinis showed this happening in their superconducting circuits, they proved that the strange rules of atoms can play out on a scale we can actually manipulate. Their discovery blurs the line between the quantum and classical worlds. It tells us there's no magic boundary where things suddenly stop being quantum. Everything in our universe, from electrons to you and me, follows the laws of quantum physics. It's just that at larger scales, those effects become hard to notice. By showing quantum behavior in macroscopic circuits, these physicists didn't just win a prize, they helped bridge two worlds. The Nobel Committee recognized their work because it completely changed how scientists designed future technologies. From quantum computers that solve problems in seconds that would take classical supercomputers years, to quantum sensors that can detect incredibly tiny magnetic or electric fields, and quantum communication, where information is passed securely using quantum principles. So, that's the story of how three brilliant scientists proved that the bizarre rules of quantum physics apply even in the circuits we can hold in our hands. John Clarke, Michel H. Devoret, and John M. Martinis showed that our everyday world is far more quantum than we ever imagined. If you enjoyed this video, hit that like button, subscribe for more science explained simply, and drop a comment below. Which quantum phenomenon fascinates you the most? Until next time, stay curious and keep exploring the universe one quantum leap at a time.